Let's talk about interoperability and safety. So memory safety in particular is really important because a huge portion of severe vulnerabilities have been traced back to memory safety issues in the past. And we want to improve the safety of our applications in general. Some regulatory bodies picked up on this problem, so there are regulations in the way to move us to a safer space, like enforce use of memory-safe languages and some mitigations in some domains. But more importantly, it is a moral imperative to improve the safety of these applications because we want to protect user data, and we want to have safer applications in mission-critical domains. So we have existing code written in some memory-unsafe languages, so we have these vast oceans of unsafe code, and the question is, how can we improve the safety? And according to some recent studies, actually most of the critical vulnerabilities are in newly written code, because we tend to find vulnerabilities in existing code over time, so they have sort of a decay. So if we cannot do, and we often cannot do, a full rewrite, the best bang for the buck is to start to write new code in a memory-safe language. So we will end up having these small islands of safe code in a vast ocean of unsafe code. And over time, we try to grow these islands. So to summarize this and to take home a point, so I want to acknowledge that we also want to make the ocean safer, and in fact we are making C++ safer, we are adding new language features, we are adding new mitigations to improve memory safety, but it is unlikely that we will get C++ to a fully memory-safe language in the near future. So what we really want to do, we want to lower the barrier to write the first line of safe code in a code base, and we want to make it as easy as possible to start those islands and to grow those islands. And to do that, we need to have better bridges. So this talk is mainly about how we build these bridges, in a particular way that it is really easy to adopt these memory-safe languages, and it is really easy to grow these islands because everything is incremental, and we can just sprinkle in a little bit of additional information and we get a little bit of additional value. So there are many different aspects of memory safety, but in this talk in particular, I will focus on lifetime safety because this proved to be a really challenging task to solve. And also, this is crucial to get right when we are interoperating with memory-safe languages. So let's talk about lifetime safety. So lifetime safety is a property that we only access objects within their lifetime. So let's look at an example. Here we create a std string, a temporary object, and we get a pointer into the buffer of this std string. And this temporary object, the lifetime of this temporary object will end at the end of the full statement. So this pointer p will dangle after this statement. So this is like a classic use after free error if we use pointer p later on. So in C++, it's quite challenging to get lifetime safety right. One reason is the confusing rules around the lifetimes of temporary objects, like sometimes they get lifetime extended, sometimes they do not, and these rules are not always intuitive. But more importantly, C++ is using a vast number of memory management techniques. So if you see a code snippet like this, we might have no idea, are we supposed to free this object that P is pointing to? Is this an intrinsically reference counted object? Is this something that has a lifetime tied to my object? Or would this pointer be invalidated later on because it's part of some memory pool? Or is this pointing to static memory? So there is a huge number of options, all of which can be expressed in C++. And what option did we choose to manage this particular object is not expressed in the APIs in any way. So we just sometimes rely on some conventions, and we have all of these techniques used in the same application because these different memory management techniques have different pros and cons performance-wise. And it makes it really challenging to reason about C++ code. Also, sometimes we have non-trivial invariants. So for example, if I have a vector, have an iterator into that vector, I push back an element to that vector, the vector's buffer might be reallocated, and then I have a dangling vector. Another classic use after free error. And it might be quite apparent in this 3 lines of code, but imagine if these 3 lines are in separate source files, even separate modules in our big code base. It's really hard to find these errors. And once we are starting to interoperate between different languages, that opens up new possibilities to introduce lifetime errors. Whenever I have a mixed code, I have a solid vertical line for C++ and a dashed one for Swift. So here we are using a C++ vector from Swift, and lifetimes of objects, the rules for object lifetimes is different between the 2 languages. So in Swift, when we see the last use of an object, that's where the compiler can end the lifetime of that object. And because this information is not there in the APIs, the compiler does not know that the vector and the iterator are related. So since the lifetime of the vector can end after this use, we will end up with a dangling iterator, and that introduces a memory safety issue. So the question is, how can we improve this situation? And one could say, let's just add the missing information to the APIs and we are done, right? So why don't we just do that? The problem is there is a big design space here with different trade-offs, and depending on what we want to achieve and what our priorities are, we might want to end up at different places in this design space. So here are some examples, like some aspects of the design space, some projections of it, and let's see what we want to get if our main goal is to make adoption as easy as possible, so we can encourage our users to start to take advantage of using a memory-safe language as soon as possible. So first of all, we want this information that we sprinkle in the code base to be incremental. First of all, the users might consume code, third-party code, that they cannot annotate. So we need to be able to interact with code that is not even annotated in the limit. And when we start to add annotations to make the interop safer, we want our users to be able to start annotating only the important APIs, start annotating only the boundaries between the 2 languages, because if we tell our users, first you need to adopt an annotation language to the entirety of your code base before you can get the benefit of a memory-safe language, well, that's not going to happen. Memory-safe languages are really great, but they are only great if they are used. So our main goal is to make sure that they are used. On the other hand, having viral annotations have a value, because virality can help us to spread these annotations, to adopt them, to get more safety. So the best way to get there is to have optional virality, so people can use these diagnostics to drive the adoption of these annotations, but they can do it on their own accord, and they can do it in their own pace, and they can do it where they see value from these annotations. We don't want to do too much inference because it makes APIs harder to understand, but even more importantly, we want adding these annotations to be rewarding. We want both the C++ code and the memory-safe code to benefit from these annotations, and if the compiler can optimize based on the presence of these annotations and can get additional undefined behavior, people can get additional undefined behavior after adding these annotations, that would be really bad because that would be punishing in some way. We never want to punish our users to try to adopt safer constructs. And as I mentioned earlier, in C++, we can express any sort of memory management techniques, and it's very unlikely we will ever have an annotation language or a type system that can express all of those. So what we are aiming for a solution that's easy to adopt, that's easy to understand, that doesn't feel foreign to C++ developers. And so we want to have this sweet spot that can express the constructs that we are interested in, but still it's something that people are willing to take into their C++ code base without being forced to write another language. Okay, so let's take a look how we can annotate lifetimes in Clang today. So there are two very similar pieces of code that I showed you earlier. And if we run this, or if we compile this today, we will get a warning for the first one, but we don't get a warning for the second one. So we get a warning for the first one for the same reason I talked about earlier. And the second one is safe. So the question is, how can Clang tell that the first one is problematic, but the second line is okay? And the reason Clang can tell that, because we have this annotation called Clang lifetime bound. And this annotation in this case specifies that the return pointer, the lifetime of the return pointer will end when the lifetime of the implicit this object ends. So using this annotation on string, Clang can tell, okay, the lifetime of the temporary stood string will end at the end of the full expression. So the lifetime of P will also, or of the lifetime pointed by P will also end. So it can generate this diagnostic. And this attribute actually been part of Clang for the last 7 or 8 years. So this is not really new, although there are some recent improvements in upstream Clang, thanks to some people at Google, to make these diagnostics way more useful. And another new annotation that was added recently by some of our friends at Google will help diagnosing this case when we try to add like a temporary string to like a string view to a temporary string into a set. And this is thanks to a new annotation that can describe that, okay, now the lifetime of a value will be captured by some other value. So this is this annotation and the diagnostics are there in the just released version of Clang. Okay, so this is what we have in Clang today, and let's take a look at what we could have that would make the situation better when we want to interoperate with other languages, but also how C++ can benefit from some of these additional facilities. So here we have a piece of C++ code. Stringref is a reference object, and we have an API that returns a stringref here. But we have no idea what is the lifetime of this returned stringref object. So it would be great if we had an annotation that would sort of force the compiler to check all uses of this type and would warn that, okay, we are returning a reference type, so we're supposed to add the lifetime annotation there. So this is the sort of optional virality that we can use to drive adoption of these diagnostics. And in fact, we did add an annotation like that so this annotation was motivated by interoperability, but as you saw, it's fairly useful for C++, even if we never consider interoperability. So this annotation is new in our fork, but let's see how this annotation is used when we are trying to use C++ code from Swift. So we see the same C++ code as before, and let's imagine we try to use some of these APIs from Swift. So we introduced a new optional language mode in Swift, strictly memory-safe mode. And in strictly memory-safe mode, when we use a foreign type, like stringref in this example, we will get a diagnostic that we are using unsafe code. And the reason why that code is considered unsafe by the Swift compiler is because the Swift compiler has no idea if this is a reference type that might have some lifetime dependencies, or if this is a value type that is self-contained and we don't need to reason about all of those dependencies. So in this case, in a strictly memory-safe Swift, we need to call out explicitly that this is an unsafe operation, and then we need to audit that code by hand and need to make sure that all of these lifetimes match up by hand. On the other hand, if we want to use this type safely from Swift, we can specify that this is a reference type, and the Swift nomenclature for that is like non-escapable, but I don't want to go in too much details about that in Swift. But let's see what happens if we add this annotation. So we will get this warning that I showed you earlier, that like we have this API that lacks lifetime annotations. And if we use this from, so if we add this missing annotation, and we now try to recompile this piece of Swift code, we will get a diagnostic, and this diagnostic will call out an actual lifetime error in the Swift code. So here the problem is normalized path is a local variable, and the lifetime of that variable will end when we return from this function, and the string ref we return depends on this local variable, so we will have a use after free error. So adding this annotation on the C++ side will enable Swift to do full borrow checking, basically. And this is a compile time, like zero abstraction thing that we get on the Swift side consuming these C++ annotations. When we look at some templated types like vector, you can see a vector of string ref supposed to be considered a reference type because it does have some lifetime dependencies, but the vector of string is a value type because it's completely self-contained. So to annotate these generic types, we have some conditional annotations where whether the type is a reference type or not depends on the template arguments. This is also a new annotation. And the last thing that we had to add, now that we annotated string ref as a reference type, when we see a function like this, the compiler will ask us to add lifetime annotations here. But here we don't really need lifetime annotations because the returned string ref has static lifetime, and the string ref that we take never escapes this function. So we added well, first of all, we generalized the Clang no escape. Previously, it could only apply to pointers. Now it can apply to arbitrary types. And we added another annotation to mark that the returned value has static lifetime. And these are new. These are new in our fork. So let's take a look at why these annotations prove to be particularly useful for incremental adoption. First of all, these annotations are not viral, so one can choose to only annotate the important APIs or the APIs at the language boundaries. So we are not forced to spread them throughout the code base, so we don't need to do like a big adoption work before we start to see the benefits. Sprinkle in a little bit of annotation and see a little bit of value, and you can do it as you wish, as you have time. They also don't need to be exhaustive. So, for example, here, min can return a reference to either of the arguments, but only one of those dependencies are annotated. So this would still be considered unsafe because we have a reference that doesn't have lifetime annotations, but at least it has some partial annotations. This is very important to allow these partial annotations because some APIs might have lifetime contracts that we cannot express using these incremental annotations. So sometimes we cannot express something. So for example, we cannot express that the return pointer has the same lifetime as the first element of this pair. We might need another feature like named lifetimes for this. And this is something that we might be interested to adopt in the future, but our goal is not to be able to express everything. Our goal is to find a sweet spot that's like, that works for people. And also we would like to be able to keep this relatively simple because C++ might need to interoperate with multiple languages, not just Swift, but also Rust and maybe some more. So we might not want to re-implement the type system of every language C++ interoperates with in C++ because we couldn't write C++ code that interoperates with all of those safe languages at the same time. So we might need a lowest common denominator approach. And very important, currently on the C++ side, we do not get the full benefits. So even if the C++ compiler has all the information it needs to detect a lifetime issue, it might not, but it's not doing full-blown data flow analysis to do that at the moment. Hopefully it will at the future, we will see. But what we are currently doing, what we are currently hoping for, if the barrier of using a memory-safe language is low enough, whenever people need this sort of full contract checking, they can use a memory-safe language to begin with, so we might not need the full analysis on the C++ side. Okay, so let me summarize this talk. Using these annotations, we can express some information that is not available in C++'s type system, and using existing Clang features, we found that we only need to add very few minor extensions to make it work surprisingly well for interop, especially because sometimes the APIs that are at language boundaries tends to be somewhat simpler than the other APIs. And both C++ and the memory-safe language can benefit from these incremental annotations. And I cannot stress this enough. The main goal and driving force behind this was the easy adoption, because we want people to be able to start growing those islands as soon as possible, as effortlessly as possible, and we don't want to see friction and pushback from the authors of the C++ code. And what we encourage our users to do is to rely on memory-safe languages when they need full lifetime contract enforcement. So that was all. I'm open to answer some questions.
Questions?
Question, is there a way already to kind of do this automatically for some easily inferable attributes for existing code, that it just automatically sprinkle the easy stuff in?
Mm-hmm. We don't have that currently, but I don't see a reason why that wouldn't work for the easy cases. It's unlikely that we would be able to infer annotations for everything, but I think there is a huge portion of code that could be automated, could be annotated automatically.
And the question, I guess there's at some point there will always be I guess a gap if you just start using it incrementally, and then there's I guess some places where there's I guess a property missing. Is there a way to know what are the things, let's say I have a code base, I start adding annotations, is there a way to know what are potential things I guess I would still need to add by essentially manually verifying or rewriting code?
Mm-hmm. Yes, so if I understand it correctly, your question is how can you tell if you still need some additional annotations?
Yeah, how do I know that I added all the annotations to make it, I guess, safe? I'm not sure.
Yeah, so I fortunately, I think in order to know that you need full contract checking, so which is something that we could add to C++ at some point, but anytime, I think when we have those guarantees that you will find all of the missing or all of the wrong annotations, at that point you have such strict checking that that would not be easy to adopt. So I think that is an inherent trade-off, that you either get something that's incrementally adoptable or you get something that's that has these full safety guarantees with full contract checking. And I don't think that you can have both. I hope I will be proven wrong, but yeah, so I think the best place to be to have the incremental version, and people could opt into the full contract checking if they want to.
All right, thanks.
Very interesting talk, thank you.
I have actually two questions. You mentioned named lifetimes, and I wonder if you kind of looked into it, explored using this instead of the attributes. And then the second one is this attribute something that you see as like feed for mainly interop boundary, or something that is potentially extendable to bring like more safety to just the C++ code base?
Yeah, so we haven't looked into named lifetimes yet, but there is a team at Google that I believe are looking really actively into named lifetimes, and I'm really excited for that work, and we'll be really curious what comes out of that. So there is some work happening in that space, but like not in our team at the moment. So the second question, whether it's only for the boundaries or whether it's useful for C++, I think this is really useful for C++. Like C++ code can have a lot of benefits from using these annotations. I think Ilya is here, and he probably has a lot of experience rolling these annotations out at Google. And my understanding is that it did find bugs in the C++ code base there. So I think it already proved to be useful for C++, even if we do not consider interop. Whether people are willing to take it in their code bases, that's a different question. How the community reacts to these annotations, that's something that we will see in the future, I guess.
Thank you.
Yeah, I'm actually at Google with the team that works on the lifetime bound annotations, and named lifetimes is a neighboring team as well. So we could probably chat about it after this. The quick reaction to this, like, we are not actually yet working on the named lifetimes, but we are actively discussing it. So there is no active work happening right now. We're actually focused on getting this control flow based analysis, at least internal, inside one function, not intra-procedural, not inter-procedural just yet. But the question that I had is actually, you had a slide where there was escapable if the type is escapable for a vector. That is a thing that we're struggling with, and maybe you have ideas about that. How do we express situations where a vector of pointers, say there is a vector of static pointers and there is a vector of pointers of the same type that have the lifetime of my function? We obviously want to have kind of like two different annotations applied to those types depending on what the annotations of, not what the annotations of TR, but rather what the lifetimes of TR, kind of like the same type, different lifetime requirements. So what if you had a template string graph, for example, that would be an owning or non-owning string graph based on something that's not in the type, like a runtime value?
Yeah.
Do you have any ideas how to deal with that?
I believe in those cases the annotation doesn't belong to the type level. So vector of string graph is always a reference type or a non-escapable type. And if there is an API that returns a vector of static string graphs, then I think the annotation that describes that, okay, this has actually static lifetime, what we return, that belongs to the API. So I think those are two different annotations, one on the type level, one of the API level. Yeah, but if that doesn't work for your use case, I would be really interested to discuss this offline.
Yeah, let's chat about it more. There is more complicated code examples where it falls apart.
Okay, thank you.
Thank you for your talk. Is there some ongoing effort to have this annotations part of the C++ standard?
Not currently. So we are relatively early in rolling this out internally. So we would like to gather more experience before we go to the committee with any of this.
May I have one last question? I'm just curious, what is the computation time cost for handling these annotations?
So the compilation time cost for the diagnostics from Clang is actually pretty cheap. They are, so the diagnostics that I showed you earlier that are already part of Clang. Okay, let's go there. Yeah, so diagnostics like this, these are on by default. So cheap enough that we get these diagnostics all the time. But once we have like something that is actually doing data flow analysis, like it is possible that those might need to be opt-in. So I'm not sure what the cost would be there. The small additions that we made, like marking a type, reference type, or value type explicitly, these annotations are also really cheap. So everything I showed you in this talk should be really cheap on the C++ side, compile time-wise. So I would expect them to be diagnostics that could be on by default.
Thank you. Let's thank our speaker again.